Hi everyone, welcome to iWave's Agilex 9 RF ADC and DAC external loopback demo. What we have here is IG G67P PCIe card-based development platform, which integrates iWave's Agilex 9 AGRW014 direct RF SoC FPGA system on module. In this video, we will walk you through the demonstration of RF external loopback between ADC and DAC using Cockpit GUI tool and also explain the RF features and functionalities. Before moving into the demo, let us take a look at the hardware and the setup. Today we are using iWave's Agilex 9 PCIe Development Platform along with the system on module and the RF data board. This is the iWave Agilex 9 direct RF system on module, which is mounted on the top of the PCIe card. Due to the fancing mounted on the top of the SoM, this is not directly visible. On the bottom side of the SoM, we have two board-to-board connectors used to connect the SoM and the PCIe card. You can also see the two RF connectors which is presented on the SoM. These RF connectors are used to connect the RF daughter card and the system on module. One of the key advantages of this approach is the end customer can replace or customize the balloon daughter board to support different frequency ranges as per their application requirements. In this setup, the RF daughter board and the SoM are already connected. On the RF daughter board, we have 4 ADC and 4 DAC. For this demonstration, we are going to connect DAC 0 and DAC 1 to ADC 0 and ADC 1, DAC 2 and DAC 3 to ADC 2 and ADC 3. This is done using SMPM to SMPM cable in the loopback configuration. Next, I am connecting the JTAG USB Blaster 2 to the development board. Next, I am connecting the Type-C debug cable to the development board. Next, I am connecting the USB Blaster 2 to the host PC. Next, I am going to connect the Type-C debug to the host PC. Before powering on the board, make sure the boot selection switch is in the JTAG mode. Next, we are going to connect 12V 5A power supply to the board. After powering on the board, we can observe the board LEDs. After powering on the board, now I am opening Quartus Prime programmer tool. Now I am clicking the auto detect and wait for device detection. Once the device is detected, click on the device and click change files. Select the appropriate jig file and give open. Our jig file includes the integrated Airtel design with HPS support. After opening the correct file, click on the file and give start. You can see the programming process shown in the top left corner. Now the programming is completed successfully. Close the Quartus programmer and power off the board. Now, before powering on the board again, I changed the boot selection switch to active serial mode. Now we need to open any terminal to view the boot prints. Today, I am using the Terraterm. After opening the terminal, we need to power on the board again. Now we can see the board is booting. I am stopping the board in U-boot stage to show the clock configurations. Both the clock generators are programmed successfully. We can see the boot prints of clock programming here. Both the RF clock generators are programmed for the sampling rate of 64 GSPS. We can also update the clock configuration files to support different sampling rates if required. Now the board is booted successfully. So next we will open the MATLAB. Open the MATLAB through DSP Builder. After opening the MATLAB, navigate to the Cockpit GUI path. Now I am launching the GUI using the Cockpit GUI command. Let us wait for Cockpit GUI. Now the Cockpit GUI is open. I can see the Cockpit GUI window. I'm giving connect to establish the connection between the board and the GUI. So now it is connected successfully. Once connected to the GUI, the GUI will display the detected sampling rate and the board status. We can see here 64 GSPS, and also in the GUI we have tile 0 and tile 1. Since it is single tile device, tile 0 is detected now. So we can see the 4 ports starting from port 0 to port 4. We have analog loopback, digital loopback and reverse loopback options. Currently we are doing the external loopback, so we are turning off. Here we can see the hardware setup. Under the hardware setup we have calibration, latency alignment and pace alignment. Now we can move to the ADC and DAC section of the cockpit. We have 4 channels of ADC starting from ADC 0 to ADC 3. Here we can see the center frequency option is there. Then the DDC gain, I'm keeping it as 1x default. And here you can see the port status, either we can keep it active or sleep. On the top side of the GUI, we can see the mode and tail selection. Today I'm keeping in cross 16 mode, and also the center frequency of the ADC I'm keeping 2 GHz and copying to the other ports also, so that all the ADC channels are at the same frequency, which is 2 GHz. Now we will move to the DAC section. Same as ADC, we have 4 channels here. Top side we have mode selection. We'll select to cross 16 mode, and also the tail selection we have here. And same as ADC, we will keep 2 GHz center frequency. Port status will keep in active. Here additionally we have DAC voltage selection. We have various voltage options. Today I'm setting to 600 millivolt, which is default, and fine tuner options also there. Here we have the NCO frequency. Today we are setting the NCO frequency to 25 MHz, which is default. I'm keeping the center frequency of 2 GHz and copying to other ports also, so that the 4 ports are kept into 2 GHz. I'm giving the DAC configure. So now we can see your DAC is configured. After DAC configuration, this icon will change to green. Similar way we will configure the ADC also. After configuring the ADC and DAC, I will open the signal viewer. So now the signal viewer is opened. After opening, give capture data. Under the tail 0 we can see 4 channels and 4 tuners. Channel 1 to channel 4, port 0 tuner 0 to port 3 tuner 0. Here we can observe both frequency domain plot and time domain waveform. I am opening the time domain plot, enabling all the channels. We can see the noise is present in the waveform. So let us do the calibration first. For calibration, go to the hardware setup and click calibration. Before calibrating the DAC, we need to disconnect the ports. Now I selected all the boards and started the calibration. So DAC calibration was completed. We'll move to ADC. So for the ADC, we'll do the OTP calibration. Here we can able to select the frequencies. Today we are going to choose 0 to 5 GHz because we selected the center frequency of 2 GHz. So I'm selecting this and giving upload. We have calibrated ADC and DAC. Let us move to signal viewer and capture the data again. So there is no data because the cable was not connected. Let us connect the cable. So now we connected the cable. Again we give capture data. So now you can see there is no noise in the waveform. We'll go to the frequency plot and click toggle all. Yes, all the 4 channels are fixed to 2 GHz, which is shown here. Let us move to the time plot. Here in the time plot, all the 4 channels are not in the same phase. The phase was not synchronized. So now we are going to align the phase. I'm going to the phase alignment section. Here we have opened the phase alignment window. I'm clicking the ADC skew. So the ADC tuner 0 skew is measured here. So I will click D-skew. Phase alignment was done now. So again we will capture the data. Yeah. Now we can see all the phases are synchronized. It is in 0 degree.
In this demo, using the Cockpit GUI, we can see that iWave's Agilex 9 wideband system-on module and the development platform are fully integrated and functioning as expected. Thank you for watching this video. For more information, please visit our website.